Hello, this is the fourth part of our discussion of routing in data networks. In this video, we'll talk about IP addressing routing in the internet. As all of us use every day, network interfaces on our hosts are assigned IP addresses. IP stands for Internet Protocol. Currently still in wide use is IPv4 addresses, which are 32-bit long addresses in the form of 4 bytes, or more precisely 4 octets. But as we are running out of IPv4 space, soon IPv6 will be more and more in use. IPv6 addresses contain 128 bits. Now, there's a dot decimal notation for specifying IP addresses in IPv4. So most of the rest of this discussion will be about IPv4. Now, each of these X's stand for a number between 0 to 225 because each is 8 bits long. Okay, for example, for METU, we could have an address like 144.122.166.169. In binary notation, it would be represented like this. I mean, this number would be, this binary number has this dot decimal notation corresponding to this. Now, usually the first 2 bytes are referred to as the network ID, net ID, and the last 2 bytes are referred to as the host ID. Especially in a class B type network address where these 2 bytes refer to the net ID, we would have these 2 bytes referred to addressing each of the hosts inside the network. Now, what do I mean by class B? Classful IP addressing was the original initial IP addressing type in IPv4. The IP address space is divided into 5 primary classes: A, B, C, D, and E. Now, in class A, as you see here, we have a net ID of 7 bits and the host ID of 24 bits. So class A addresses can support very large size networks. On the other hand, class B has network ID 16 bits and still medium-sized networks can be supported with this. 2 to the 16 is a large number. A lot of organizations in the initial days of IPv4 just got themselves class B addresses, but this led to a quick depletion of class B addresses. For example, our university, METU, has a class B net ID 144.122. Now, because of this, first of all, let's talk a little bit about how IP addresses are assigned. There is this DHCP. I'm sure all of you noticed it when configuring your internet connection. Dynamic host configuration protocol is a network protocol that enables a server to automatically assign an IP address to a computer from a defined range of numbers, a scope configured for a given number. A subnet mask is a number that defines a range of IP addresses that can be used in a network. A subnet mask hides or masks the network part of a system's IP address and leaves only the host part as the machine identifier. A common subnet mask for a Class C IP address is 255.255.255.0. So everything except the last octet is masked. Now, let's take a look at an example routing table for a Windows 2000 based host, not a router. This host has a single network adapter which has the IP address 157.55.2790 and a subnet mask 255.255.2400. The default gateway for this node is seen here with this IP address, and to go to different destinations, possibly there are different gateway nodes. This is a routing table. As you can see, this is a network that is directly attached to this host. This basically, for broadcast purposes, this network is used. And let's see. There are different interfaces for different gateway nodes. Okay, in this case, the interface addresses all except the default route have identical addresses to the gateway nodes. Now, in network address translation, abbreviated as NAT, one uses local IP addresses inside the domain, and when going outside the domain, the NAT router translates the address from the local area network into a valid address for the wireless area network. So there's a NAT router which translates the address from the local area network into a valid address for the wide area network. So often, inside a local area network, we use dummy IP addresses. The addresses specify 2 machines at each end, while the port numbers ensure that the connection between the 2 computers has a unique identifier. The combination of the addresses and the port numbers defines a single TCP/IP connection. Each port number uses 16 bits, which means that there are 2 to the 16 possible values for port numbers, which are often, for practical purposes, almost always sufficient. Now, we'll talk more about TCP in later lectures. Now, realistically, since different manufacturers map the ports in slightly different ways, of course, you can have, you expect to have fewer number of possible values for the ports. Okay, now let's talk a little bit about hierarchical routing, which is the default routing structure in today's internet. Now, as we said, each network interface has an assigned IP address when connected to the internet. When a host wants to communicate with another host on the internet, the source needs to know the IP address associated with the destination. So it inserts the address in the headers of the packets intended for that destination. Now, when a router receives a packet, it checks the destination IP address of the packet contained in the packet header, and then looks up the routing table to locate the next router to which the packet should be forwarded. Now, a routing table has at least 2 pieces of information fields: the destination and the interface to the next hop router. The destination field specifies the IP address of the destination, and the next hop field specifies the interface to which the packet should be forwarded to reach the next hop router. Now, given the size of today's internet, it is not scalable to maintain a separate entry, of course, for each host on the internet in a routing table. Routers are therefore organized into some autonomous systems. In this picture, we see several autonomous systems. Each autonomous system consists of a group of routers under the same administrative control and is associated with one or more CIDR blocks. Remember, CIDR stands for classless interdomain routing protocol. Now, under hierarchical routing, each router outside of a autonomous system needs to only maintain a single entry for the autonomous system instead of one for each host in the system. So router C will only need to maintain an address for router A and not to every individual host in the autonomous system represented by router A. Okay, now, all right, so to go to all of these different destinations, for example, to go to this host and that host, which are different destinations inside the autonomous system represented by router B, it is sufficient to use the address corresponding to router B. Now, so a packet is first routed to the destination autonomous system using interdomain routing, and then to the destination host in the autonomous system using intradomain routing. So this mechanism is, then again, let's repeat, it's known as hierarchical routing. So intradomain routing is today, and for a long time now, has mostly been done using these two alternative routing algorithms, OSPF and RIP. Intradomain routing is routing between nodes under the same administrative control, and it is often cost-based. So we can use our Dijkstra or Bellman-Ford ideas to solve this cost-based routing problem. Specifically, OSPF is link state based, and it's based on Dijkstra's algorithm. Using broadcast information, each router computes the full topology and the minimum cost routes to all other routers. On the other hand, RIP is a distance vector-based approach based on the Bellman-Ford algorithm, where routers exchange routing information every 30 seconds and update their routing tables using Bellman-Ford. Okay. Now let's talk a little bit more about CDIR, the Classless Interdomain Routing Protocol. Now, classful IP addressing architecture in IPv4 caused a quick exhaustion of IPv4 addresses. There's room for about 4.3 billion IPv4 addresses, and currently we have pretty much exhausted these addresses. A temporary solution, of course, before IPv6 was CDIR, which can support a net ID of arbitrary length. So here's how it works. A CDIR block represents a range of IP addresses, and it is in the format A.B.C.D/X. A, B, C, D are the octets, as usual, that range from 0 to 255, and X specifies the length of the net ID. And the length of the net ID is allowed to be between 0 to 32. So anywhere between 1 bit essentially to all 4 times 8, 32 bits in this can be considered a net ID. Now, for example, all addresses in a Class B network would be represented with a net ID of 16 bits. Now, with the CIDR protocol, multiple ASs can be combined into a supernet if they share a common prefix. For example, Autonomous System 1 with CIDR block 130.126.00/16 and Autonomous System 2 with CIDR block 130.127.00/16 can be combined into a supernet with CIDR block 130.126.00/15, since the first 15 bits of these two CIDR blocks are in common.